Hello everyone, I'm Wei Du. Today I'm introducing you to the multi-resolution A-star algorithm. This research is conducted with Farhan Islam and my advisor Maxim Likachev from the Search-Based Motion Planning Lab at Carnegie Mellon University. The completeness and efficiency of search depends dramatically on the size of the discretization. Assume we have a point robot which always lies at the center of cells. On the left of figure A map is discretized into two resolutions, and expanded units are marked in blue. A coarse discretization is taking the narrow passage as infeasible, and hence search expanded the first row and exited. However, a finer discretization on the right recognized the path through the narrow passage. Figure B shows a cul-de-sac. On the left is a coarser resolution map where planar only takes 4 expansions to escape the local minima. On the right, planar takes around 100 expansions before it can exit the cul-de-sac. These two cases show that coarser resolution leads to faster search but potential incompleteness. Finer resolution leads to stronger completeness but slower search. So we are wondering, why not use different resolutions at different places of the map? The most related works are methods regarding adaptive resolutions or multiple levels of hierarchies as listed above. One famous algorithm is the party game algorithm, which iteratively divides the near obstacle region into higher resolution every time it fails to find a solution. The other type of algorithm is searching in hierarchical structures, such as chord tree data structures. These algorithms perform well on sparse environments when it comes to highly occupied environment. They perform even worse than searching on a high-resolution map. These algorithms will eventually reach a high resolution with extra computation costs such as bookkeeping the relative positions between cells. Apart from that, these algorithms cannot be easily scaled to high-dimensional planning problems. In these problems, MRI-star has the advantage of planning with different resolutions without constructing the mapped structures mentioned above. The key idea of multi-resolution A-star is simple, which is searching along each resolution at the same time, while sharing partial solutions found. Here is how partial solutions are shared. We have a map discretized into two resolutions in gray and yellow respectively. In figure A, state S0 in high-resolution space is expanded and states S1, 2, 3 are generated and inserted into high-resolution space Q1. Since state S2 also lies at the center of a coarser resolution unit, it will also be inserted into low-resolution space Q2. In figure B, we expand state S2 from a coarse resolution space, and successors S4 and S5 are generated. Since S4 and 5 also lie at the center of a fine cell unit, they are also inserted into high-resolution space as well. Hence, coincided states are shared between searches. And furthermore, segments of paths are shared. This is similar to state sharing in alternation method and multi-heuristic A-star. So this is the process of multi-resolution A-star, which is trivial to implement. It can also automatically figure out when part of a solution has to lie on the finer resolution and when the local minimum can be filled on a coarser resolution. Besides, it can provide completeness and bound suboptimality with respect to a user-specified resolution referred as an anchor resolution. Here is a simple example of how this algorithm works on a 4-connected grid map. This time, we have two resolutions in gray and orange, respectively. The heuristic is Manhattan distance. In figure A, the search started at state A2. In figure B, A1, B2, and A3 are produced as successors of A2. They are inserted into high-resolution queue. Apart from that, B2 is also inserted into low-resolution queue. In figure C, state B2 is expanded, its successor E2 is generated and inserted into both Q1 and Q2. As the search continues like this and reaches goal state, in figure G, a solution is found and composed of segments from different spaces, as you can find in red and purple. This is benefited from sharing the states. The MRI star search follows the structure presented here. Assuming the domain is discretized into multiple resolutions indexed from 0 to n, then we run weighted A* search in each resolution space from 1 to n. In addition, we have an anchor search, which is an optimal search running with resolution 0. The inequality on the right is used to control the inadmissible expansions with respect to anchor search. Then we compare the key 0 from anchor space with key I from search I. If the anchor condition is satisfied, a state will be expanded from the ith search, otherwise anchor search. Furthermore, we have a scheduling policy to decide on from which search to expand states. The scheduling policy can be round-robin style or dynamic Thompson sampling, etc. In the end, MR star stops when goal is found by any search or when null spaces are exhausted. Here are the properties of MR star. Firstly, since MR star only expands a state once in one space, then theorem 1 holds. Secondly, the search stops when the solution is found or all spaces are exhausted, so it is complete in the union space of all resolutions. At last, since all searches are controlled by the anchor condition, the solution cost from any search is bounded as in theorem 3. The details of the proof are presented in the paper. Resolutions should be selected to largely overlap the spaces so as to facilitate sharing. The size of a coarser resolution could be multiples of a size of a finer resolution. Hence, the center of a low resolution unit will always coincide with the higher resolution unit. On the first row of the figure, the map have resolutions at 4 meters and 12 meters, so there are states such as S2, S4 are overlapped between different spaces and thus shared. On the second row of the figure, when the map is discretized with 3 meters and 5 meters resolution, there will rarely be transitions between two resolution spaces, because states like S0 will largely exist in high resolution space, whereas S1 will only exist in low resolution space. Then, how do we select the resolutions for anchor search? There are 3 types of choices. The first is using the highest resolution. It can provide tighter optimality bound than mid-level resolutions, because the optimal solution on higher resolution map is more similar to the real optimal solution. Also, in the anchor search, we only consider the set of actions that could be used in high resolution space. However, when the anchor space is exhausted, there will not be any bounds for the solution found later. We can also choose the mid-level resolution. Then the anchor search will march faster because of larger step size, and anchor search will only consider the set of actions required in mid-level resolutions. But similar to using high-level resolution, there will be no bounds for the solutions when anchor search exhausted. And compared to high resolution space, the optimality bound will be looser. To always provide suboptimality bounds for the search, we can choose the union of all resolutions as anchor resolution. It will always provide bounds because union space is the last space to be exhausted among all spaces. On the other hand, the search in union space will require actions in all resolutions, which increases the branching factor as well as the computation load. Here are experiment results. The performance of planners are evaluated in terms of success rate, planning time, and mean cost. Firstly, we implemented the algorithm on 2D maps. The map size is 10,000 by 10,000, and we have resolutions in 1 meter, 7 meters, and 21 meters. We have baseline algorithms weighted A* searching on a single graph combining all resolutions, denoted as weighted A* MR, in highest resolution, denoted as weighted A* high, and lowest resolution, weighted A* low. Besides, we have implemented called tree search, denoted as QD tree. Baseline algorithms are using weight as W2, so all algorithms have the same bound. As you can find on table 1, In both maps, MRI star consistently have highest success rates. In terms of mean planning time, it only runs slower than weighted A star in low resolution and cold tree search. However, weighted A star in low resolution is not complete and thus failed a lot. Cold tree search is implemented on an explicit graph, which is pre-built and saved time of constructing new states during planning, but the pre-computation cost is around 9 seconds on these large maps. And then we conducted our experiments using a PR2 rubber arm in 4 scenes: kitchen, bookshelf, industrial, narrow passage. The angular resolutions for each joint are discretized into 3 degrees, 9 degrees, and 27 degrees. The results for each planning scene are documented separately. The baseline algorithms are weighted A star search on a single graph combining all resolutions, weighted A star search with adaptive dimensionalities, RT Connect, and RT star given 120-second time limit. In terms of success rate, MRI star consistently have high success rates in all scenes. Besides, MRI star is faster than other search-based algorithms and RT star for most of the time. Although it is not as fast as RT Connect, the solution quality from MRI star is much better than RT Connect, and even better than RT star. The improvements shown below is consistent with the results from 2D planning. There is a significant improvement in planning speed, but not that much improvement in cost. To conclude, we proposed MRI star algorithm for planning tasks in large state space. MRI star obtains fast planning speed by searching multiple resolution spaces and sharing partial solutions between them, and we have presented that MRI star is complete in the union search space and could also provide solutions with bounded quality. Although MRI star performs well in most of the test cases, there are still some interesting areas to be explored. For example, it is worth trying to incorporate a multi-resolution A star framework for other bounded suboptimal search algorithms, or applying MRI star to high-dimensional kinodynamic planning. In the end, thank you for attending my presentation.
My name is Nathan Sturdivant. I'm a professor at the University of Alberta, and today I'm going to present joint work with Malte Helmert on budgeted tree search. This is a new algorithm that's been recently invented, and we're presenting this as a position paper at SoCS, and it's a companion to original work that was published that has a lot more details on the broader applicability of a general idea called IBEX. We're just looking here at the specific instance of budgeted tree search. So we're going to answer two questions today. Why do we need budgeted tree search, and how does budgeted tree search work? In order to do that, we're going to look at an example state space, which is a 3x2 sliding tile puzzle. We'll use this throughout the talk today. The goal is that we have a start state, and we want to transform this into the goal state by taking actions one at a time. We have a heuristic that estimates the number of actions that we'll take to get there. And then we're going to, by applying actions, going to try to find actually the optimal sequence of actions that takes us between the start and the goal. Okay. So generally speaking, a search problem is defined by a start state, a goal state, a successor function, and a cost function. And these four things put together give us an implicit graph. So many problems will not fit in memory. Therefore, we'll need to use something like a depth-first search to be able to fit the problem in memory, and we get that from this implicit graph. And then we also have a heuristic function, which is estimating these costs. There's some properties on here I'm not going to go into today. But the goal, at least for today, again, is to find optimal paths between the start and the goal. So the first question we want to answer is, why do we need budgeted tree search? And in order to understand that, we need to look at IDA star, which is the algorithm that we're going to be comparing against. IDA star is an algorithm that does iterative deepening on F costs, where F costs are estimates of the optimal cost from the start to some node n, and then from n to the goal. And so the G cost is the cost from the start to n, the H cost is the estimate from n to the goal. And the idea is that IDA star is very conservative when it searches from the minimum F cost and then the next greatest F cost, and continues and does iterative deepening iterations with each possible F cost. Let's look at how this works. So this is an IDA star search tree, and in this problem we're going to show the equivalency between the search tree and the actual sliding tile puzzle on the right-hand side. And what we can see here is a couple of things. The nodes that are highlighted in blue are the nodes that will be searched as part of the current iteration. The color of the nodes in the tree tells us what the F cost is. So in this particular instance, we have 3 possible F costs in the tree, and now we can watch the search run. So it's going to search in a depth-first manner through the current tree, and it's going to continue this process until it goes down and it finds the goal on this branch. So that's how IDA star works. And IDA star has been a successful algorithm in practice because of a few things. So the first thing we notice here is that when the F cost, so when we look at how many nodes for a given F cost, we're going to count how many nodes there are, or how many states there are in the state space with that particular F cost. And so we see for F cost 11 that we have 2 states. When we have F cost of 13, that grows to 16 states, so that's growing by actually a large factor, a factor of 8. And when we go to F cost 15, we get to 79 states in the tree. And so that's growing by a factor of 5. And as long as that grows by a constant factor, then we see exponential growth in the tree. Now, IDA star assumes that there will be exponential growth. And if you do, what you see is you start with 1 node at the root, and then this is going to grow b nodes, b squared, b cubed, all the way up to b to the d, where b is the branching factor. And when you grow exponentially like this, here we're multiplying by a factor of b, then it ends up that the overhead of doing the multiple iterations is amortized away, or is less than a constant factor. If the F costs only grow linearly, then we see something different happening. We would start with 1 node, but then we may only see 2 or 3, 4, 5 in our iterations. And when you add those up, you get b to the d squared. So this is going to be really bad in practice. And this can actually happen, and we're going to show one way of it happening when we use edge costs that are just slightly different than the unit edge costs that are typically used. So here, the cost of moving a tile is determined by the tile itself. So tile 1 has cost 1.5, where tile 9 has cost 1.1. And when we do this and run IDA star, what we see here, now we're running very fast, but we see here that the tree is actually still growing very slowly. And the reason why is that in this tree, I'm not going to let this finish, but in this tree, we don't have many states with the same f cost. Actually, most nodes have unique f costs. So the first iteration is one node. The second iteration would be two nodes, those with f cost 11 and 11.25. Then three nodes, including 13.45, four nodes with 13.5. And so, in fact, this is exactly the worst case by using such a simple cost function here. Each of our iterations is just one node larger than the previous iteration. And so why do we need budgeted tree search? Well, if the nodes in each iteration do not grow exponentially, then we need something like budgeted tree search to make sure that they do grow exponentially. Okay. So the big question here that we see is, where do we get the next bound for search? Well, in the past, IDA star was the most conservative approach you could use, which is use the minimum possible next f cost. And so that works when you have unit edge costs and the tree grows exponentially. But there has been work that looked at other approaches where they try to estimate how much the f cost bound should increase. There's also been other work that looks at what happens if you have a different type of state space. Maybe it grows polynomially instead of exponentially. In this paper, we showed that you could grow with a different process to be able to get this exponential growth that we wanted. And so all of these approaches are nice. They work in very certain circumstances. But the problem is that we want to guarantee that no matter what the tree looks like, we're going to see exponential growth in the number of node expansions we perform. And so I want to show here what we'd like to have, which is an oracle that would tell us what we need to do in practice. So here we have f cost equals 11. For the root of the tree, we do one node expansion. What we'd like is an oracle that tells us how we can make the tree grow. And in this case, what we're going to see is that the tree needs to grow either at least by a factor of 2, but no more than a factor of 8. So we're going to put some constant bound. Those could be different constants, but for this talk, it'll be 2 and 8. So we ask our oracle, and our oracle says, look, if you just increase your f cost to 11.25, you'll do 2 node expansions, which will be within that limit. And we could ask the oracle again. So we do a depth first search here. We ask the oracle again. We say, now give me the next f cost, where I'm going to do 4 node expansions, because we want to avoid this linear behavior. And the oracle would say, well, if you want between 4 and 16 node expansions, then use 13.97. That'll give you 11 nodes. Again, we continue. Now we want between 22 and 88. And the oracle would say, use 17.17. That'll give you 47 nodes. And if we can continue this process, we would see the tree continue to grow exponentially until we find the solution. And then we'd be able to terminate, again, with the optimal solution. Now, we're going to be able to use an approach from 1976 called Exponential Search, and we're going to use that to build an oracle. So we want to build an oracle that can tell us what next f cost to use, and this oracle we're going to show is not very expensive in practice. Okay, and so this algorithm is going to assume that we have an array that is unbounded in length, but the items inside it are sorted, and we're going to look for some item inside it. In this case, the blue item here, that's the blue square. And what this does is it is going to query, and it's going to get back when it makes a query. So it's going to query an element in the array, and it's either going to be told it's too small, it's too large, or you found the element. So we query the first item, we query the second item. Both of these we're told were too small. And again, if we did this in a linear way, we would get a linear amount of work, but we can do better than that. Because now we're going to start growing this exponentially. So the 4th element, the 8th, the 16th, the 32nd element, and all of these we get back that we're below the bound. And then we continue here, and now we have a new query where it tells us it's above the bound. And then from here, we can just use a binary search to look inside here and find the actual element that we want. All using these these queries that tell me less than or greater than the value that I'm looking for. And the running time, because the bound is the steps that we're doing in the array are growing exponentially, then it'll take log steps to get to the value, and then it'll take log steps to do the binary search to actually find it in the worst case. Okay. So what we're going to notice here is that there's an equivalency between this algorithm where we have f costs. F costs are going to be our unbounded sorted array where we have all possible f costs. There's some numerical accuracy. I'm not going to talk about that here, but that can be dealt with. And then we're looking for values, and the values we're going to be storing are the number of node expansions that are performed for each f cost. So we don't know for a particular F cost how many nodes are expanded, but we could actually just run a depth first search or a bounded depth first search, and we could tell it the answer. And the important thing here is that node expansions, as they increase the F cost, the node expansions are also going to be non-decreasing. Okay, so how does budgeted tree search work? Well, we're going to do something like an exponential search on F costs, and this is going to be the key operation. But we're going to add something called a budget in here that's going to make it efficient. So we have our F costs, we have some range that we're trying to find, some range of F costs that cause us to go from 2 times to 8 times the number of node expansions. In this case, if 100 is the number of nodes I did at F cost 10, then I want somewhere between 200 and 800 node expansions. Anything that's less than 200, we could sample those F costs. It would cost less than 200 to do that. Anything that is greater than 800 could be arbitrarily large. It could be that we sampled the F cost of 32 and we did 1 billion node expansions, and we'd like to avoid that. So what the budget is going to say is, look, all we want to know is, are we less than, or are we equal to, or are we greater than this bound of windows that bound the amount of work we want to do in order to grow exponentially. So if we have an upper bound that says we want to do no more than 800 node expansions, then once we've done 800 node expansions and not actually solved the problem, we'll know we're in this upper range of more than 800 nodes, and then we can stop the actual search. So the most we're ever going to pay when we do this sampling is actually this upper bound. Okay, so that's our budget of 800. Okay, so again, let's look at this, set up the same problem here, and this is what we're looking for. So we're going to sample 10 we know is 100 nodes, so now we're looking for something between 200 and 800. So we sample 11, we sample 12, 14, 18, 26. All of these are less than the bound. We sample 42, which is greater than the bound. And again, when we sample this, what we're actually doing is we're doing a depth first search that is bounded by an F cost of 42. This will terminate when we hit 800 node expansions, and then now we'll be able to do a binary search until we find that we fall within the final window that we want. Now, the running time of this for one iteration here is that I have the most I'm going to pay is this maximum bound, which in this case would be 800 nodes. That would be n of I. And then the F cost that I'm trying to find, it's going to take at most log of that steps. So the F cost for the ith iteration. Now, overall, when I'm finding the solution, I have to do this for all iterations I. And if we look at this overall, what we see is that the final F cost is bounded by C star, the optimal cost. And then if we sum up the set of n of i's, well, we know because they're growing exponentially that they'll sum up, that they'll be asymptotically, they'll be equal to n. And so the running time then of this algorithm, in the worst case, is n log C star. So how does BTS work? Well, the first thing we're going to do is we're just going to run IDA star. That is, we're going to be conservative and we'll use the minimum F cost possible. And therefore, if we have a problem where IDA star is the right thing to do, we want to be conservative, then we'll just use IDA star every step and we'll actually go no further. We'll see the exponential growth in the tree, and the behavior of BTS in this case is exactly identical to IDA star. However, if IDA star fails with the conservative F cost to grow the number of nodes exponentially, then we're going to start growing the F cost exponentially with a constant budget. And if we grow the F cost exponentially and we find the solution within the budget, or sorry, find a F cost that searches the number of nodes we want, then we'll be done. But if we exceed our budget, then we'll do a binary search. Okay, so let's look at how this works in practice. These are the new 2 steps that do not exist in IDA star. They're what we can add to IDA star to get the performance that we want. So here we see IDA star. In the previous iteration, it has done 13.97 was the F limit, and it expanded 11 nodes. It was trying to get between 4 and 16, and so that worked out. So when we come into the next iteration, as I said before, we had 13.97. Now we're going to use an F limit of 14.0, and that's simply what IDA star would do. That's the next possible F cost limit, and we're looking to do at least 22 node expansions. And when we do that, we're going to search this little tree up here, and we see, you know what, we only did 12 node expansions. That's below the window that we're looking for of 22 nodes. So now we're going to switch, and we're going to do an exponential search. And the exponential search, basically what we're going to do is we're going to start taking the lower bound that we have, in this case 14.2, because that's the lowest F cost that hasn't been explored yet. And we're going to start adding an exponential term to it. In this case, it's 2 to the 0, which is going to give us 15.2. And when we search with that, we're going to go across this tree. We expand 18 nodes. 18 is still less than 22 nodes. And so now what we can do is we have to continue to search. So now we're going to increase this bound from 2 to the 0, 2 to the 1. And actually, we've increased our lower bound from 14 to 16. So we're going to use this lower bound of 16.2. We search with 18.2. And here we go across the tree. And what's going to happen here is that we're going to hit our node limit. You can notice actually the search is going back up the tree. This is because it's strictly not a tree. I'm drawing the tree on the screen, but there's actually a search tree is being searched here. And we hit our node limit of 88 nodes. And so we run out of our budget and we have to stop. And now we're going to turn and do a binary search. So now I was using 18.2 for my search, but the maximum of cost I actually saw was 18.15. And so now I'm going to look at my two bounds. I know it is no less than 16.2. I know 18.15 is actually too high. So I'm going to split the middle and I'll search with 17.17. And when I do that, searching with 17.17, I'm going to come across the tree here and I will complete this entire iteration. I don't find a solution, but I've completed the iteration with 47 nodes, which is growing by at least a constant factor. Okay. So how does budgeted tree search work? Well, it's IDA star, except that when IDA star fails to cause the tree to grow exponentially, that is the conservative bound of IDA star, we're going to increase it exponentially. And then we'll do a binary search if we need to, but using a budget on these searches to ensure us that we don't pay too much cost when doing these searches. If we compare the two approaches, we see IDA star on the left, budgeted tree search on the right. Budgeted tree search aggressively increases the size of the tree and then draws it back if it needs to, and budgeted tree search is able to find the solution quickly, much more quickly than IDA star. And budgeted tree search may have to search the last iteration in its entirety, and that's just because it has to prove that it's found the best solution when it's found it. And we won't, in this case, watch IDA star finish. To summarize, budgeted tree search reduces the worst case of IDA star. If the tree grows exponentially, it'll behave exactly the same as IDA star, but otherwise it'll have a much better worst case. And IBEX is a more general algorithm that will solve similar problems in different contexts. And if you're interested in exploring this more, I have single agent search demos available on my webpage, and you can find one of these demos on budgeted tree search. You can also download the movies that were used in this talk, as well as the individual frames if you'd like to use them for teaching or for other purposes. Thank you for coming, and if you have any questions, feel free to email me. Thank you.
Hello everyone, I'm going to present you the paper called A Simple and Fast Bi-Objective Search Algorithm, which will appear in the proceedings of ICAPS 2020. The paper has a number of authors, Carlos, William, Han, Luis, and Sven. Before continuing, I'm going to introduce you to the problem. The bi-objective search problem is a form of graph search in which the objective is to reach a goal state from a start state. The main difference with traditional search is that there are two objective functions that need to be optimized. So for example, in robotics, these two functions could be the distance traveled and the battery consumed. In road networks, there are various interesting combinations. One might be interested, as usual, in minimizing travel distance, but also in minimizing travel duration, or if you're carrying hazardous material, you might be interested in minimizing the number of people that could be harmed in the event of an accident. To compare two paths that reach the goal, or any two paths in this kind of search, we use a vector of values. So if this is the A B is the cost of a path and A prime B prime is the cost of another path, we say that one path dominates the other if this relation over here holds. So given this domination relation, when we're solving a problem, we're not looking for just one solution, but a set of solutions that are non-dominated solutions. So no pair of solutions in this set dominates another one. In the state of the art of this problem, we find the algorithm NAMOA, DR, which we call this way in this paper. It was proposed by Pulido and colleagues in 2015. In our paper, we propose a different algorithm, which is called bi-objective A star, and we like to call this algorithm BOA. The algorithm improves over the state of the art by making some of the dominance checks more efficient. So for example, when we find another state during the search, when we find a state that has been found before by another path, we need to check that the new path that we have found dominates the other one, or to check whether the new path is non-dominated by the paths that have been found before. So this kind of check, we do it in constant time, whereas other algorithms would require linear time to make it. Also, when we have found another solution, we need to check that the new solution is not dominated by solutions that have been found before. Such a check is also carried out in linear time by our algorithm. Another feature of our algorithm is that it's quite simple. If you look at the pseudocode, it will resemble A star pretty much with a few changes. Unlike other algorithms that need specialized data structures that are not, that related to aspects that you usually see in A star. Finally, in our empirical evaluation, which I'm going to show you a little bit of that now, we show improvements quite significant with respect to the state of the art. We actually compared in 5 roadmaps of this competition. In the Great Lakes map, which is shown here, which contains more than 2 million states and more than 6 million edges, we here show in the red curve the performance in terms of runtime of BOA and the other algorithms. And we see that there's a very significant improvement compared to the other algorithms. This improvement is also seen in other benchmarks. So to summarize, I presented to you BOA, a A-star-based algorithm for bi-objective search, which improves over the state of the art quite significantly by making domination checks very efficient, actually in constant time compared to linear time required by other algorithms. Thank you very much for watching the video.
Hello everyone, my name is Shachaf and I would like to talk to you about the differences and similarities of FMM and GBFHS. This is a joint work with Professor Ariel Fellner and we are both from Ben-Gurion University. Before talking about differences and similarities, we first need to introduce our two main players, FMM and GBFHS. We'll begin by talking about the meet-in-the-middle algorithm by Olte et al., which is also known as MM. MM is a bidirectional heuristic search algorithm that is guaranteed to meet exactly in the middle. That means that MM never expands nodes whose G value exceeds C star divided by 2, where C star is the cost of the optimal solution. Essentially, nodes outside of these two circles will never be expanded by MM. To ensure this property, MM uses a priority function to expand nodes. On each iteration, MM chooses a node for expansion that has a minimal priority value. It can be either from the forward frontier or from the backward frontier. The priority of a node is equal to the maximum between its f value and twice its g value plus epsilon, where epsilon is the minimal edge cost. And if this information is not available, then you can simply assume that epsilon is equal to 0. Fractional MM by Shacham et al. Is a generalization of MM to different meeting points. FMM uses a fraction p, and given that fraction between 0 and 1, it never expands nodes whose g value from the forward side exceeds p times c star, and whose g value from the backward side exceeds 1 minus p times c star. This means that nodes outside of these two circles will not be expanded by FMM. FMM also uses priorities, but it has two different priority functions, a priority for the forward side and a priority for the backward side. The priority function is the maximum between the f values and the g value divided by p plus epsilon for the forward side, and g divided by 1 minus p plus epsilon for the backward side. If you consider p to be 0.5, which is essentially meeting in the middle, then both priorities become 1, which is the priority function of MM. To demonstrate the execution of FMM, we will use two examples, EX1 and EX2 on the next slide. Both of them will accompany us throughout the entire presentation. For simplicity, we'll use p equal to 0.5, which is MM, and this is the priority function of MM again. This example is a unit edge cost example, in which the value within the nodes is equal to the heuristic value, and the arrow indicates the direction of the heuristic. For example, this is the heuristic value from getting from start to goal. At the beginning, the priority of both start and goal is equal to 2 because of their f value, and therefore FMM can choose to expand either one of them. After start is being expanded, nodes A and S1 are generated. A has a priority of 4 because its f value is equal to 4, and S1 have a priority of 3 because their f value is equal to 3. So now goal has the lowest priority and it will be expanded. And G1 and C will be generated, which are symmetrical to S1 and A. Now S1 and G1 both have a priority of 3, therefore FMM can choose to expand F1 with S1 without loss of generality, and generate S2. The priority of S2 is equal to 5, because its G value is equal to 2. And if we look at the priority function, 2 times 2 plus epsilon, where epsilon is 1, because this is a unit edge cost problem, is equal to 5, and this is the priority of S2. Now G1 has the lowest priority, and it therefore expanded. Now FMM can proceed to expand A and C, and find the optimal solution. I would like you to remember that in this example, FMM had to expand the G1 nodes before being able to terminate. In this example, not all edge costs are equal to 1, and the edge costs are written above the edges. For example, the edge between A and B has a cost of 0, which is also the minimal edge cost. So at the beginning of the search, start and goal both have a priority of 2 due to their f values. So start can be expanded, and A and C are generated. A has a priority of 4, and C has a priority of 3, and the priority is induced by their f values. Now goal has the minimal priority, and it is therefore expanded. And D and B are generated, which are symmetrical to C and A. Both C and D has the minimal priority values, so they need to be expanded before moving on to expand A and finding the optimal solution. Here I want you to remember that D had to be expanded before an optimal solution was found. Now it's time to introduce GBFHS by Barley et al. GBFHS can also set a meeting point between the two frontiers, but it is doing so using a split function rather than a fraction. It maintains a bound on the solution cost, flim, and it splits that flim value into a forward and backward limits on the g value, such that flim is equal to glim forward plus glim backward plus epsilon minus 1. The split function determines the exact values of glim f and glim b. GBFHS then expand nodes in direction d with g value strictly less than the corresponding g limit, and f value less than or equal to the f limit. Now let's look at the execution of GBFHS on example 1. Recall that the f value of start and goal is equal to 2, and this is why f limit is initialized to 2. Furthermore, epsilon is equal to 1, and therefore the f limit is equal to the sum of g limits. Since we are aiming at meeting in the middle, we'll consider split function that tries to balances between the forward limit and the backward limit. In this case, both of them are equal to 1. This means that the nodes which are eligible for expansion have f value which is less than or equal to 2, and g value which is strictly less than 1. Therefore, both start and goal are eligible for expansion, and GBFHS needs to expand both of them. Now, A, S1, C, and G1 are generated, and since the minimal f value in the open list is equal to 3, the f limit is increased to 3, and one of these bounds needs to be incremented. Without loss of generality, the forward bound will be incremented first. So now, the only nodes that fulfill these conditions with respect to the new values are the S1 nodes, and GBFHS must expand them. Now there are no other nodes which fulfill these conditions, so the f limit is increased. At this point, both A and C fulfill the conditions, and GBFHS can expand them and find the optimal solution. Note that this time, GBFHS did not have to expand G1 before finding the optimal solution, as opposed to FMM who had to expand G1. Now let's move on to the second example. Here too, the f limit value is equal to 2, because of the f values of start and goal. However, this time, the sum of glim forward and glim backward is equal to 3 instead of 2. This is because, in this example, the value of epsilon is equal to 0. Now, the nodes which are eligible for expansion must have an f value which is less than or equal to 2, g limit in the forward direction which is strictly less than 2, or g limit in the backward direction which is strictly less than 1. Both start and goal fulfill these conditions, and therefore GBFSH can choose to expand start and goal. Now the minimal f value in the open list is equal to 3, thus the f limit value is updated, and the glim backward value is incremented. So now the only nodes which are eligible for expansion are C and D, because they have an f value of 3 and a g value of 1 which is strictly less than 2. So GBFSH must choose to expand C and D before being able to increment the flim value and expand A. After expanding A, an optimal solution was found. Note that just like FMM, GBFHS had to expand D before finding the optimal solution. In order to compare the algorithms in a more formal way, we define M and E of algorithm A given a problem instance I to be the minimal number of node expansions required by algorithm A to optimally solve I. This essentially means running A using the best possible tie-breaking, which is of course not known in advance. Recall that GBFHS, when running on the first example, did not have to expand the G1 nodes before terminating, while FMM had to expand them. This is why the M and E value of GBFHS is strictly less than the M and E value of FMM. Furthermore, we have a theorem in the paper that shows that for every problem instance I, the M and E value of GBFHS is less than or equal to the M and E value of FMM. This means that GBFHS dominates FMM with respect to M and E. Since FMM uses a constant fraction that remains the same throughout the search, while GBFHS uses a split function which dynamically updates the values every time the F-limit is increased, we can generally compare between the two. So we need to define a new version of FMM, which we call DFMM, dynamic fractional MM. DFMM is exactly the same as FMM, except for the fact the fraction can be updated. This means that the fraction is updated every time the minimal priority is changed. Other than that, DFMM uses the same priority function and stopping criteria of FMM. Also, note that FMM can be represented as DFMM because we can simply keep the fraction constant throughout the search. Now let's talk about lower bound on paths. Given admissible heuristic, a node U in the forward direction and a node V in the backward direction, LBUV, which is defined to be the maximum between their F value and sum of G values plus epsilon, is a lower bound on any path that goes from start to goal through U and V. We can use that bound between pairs to define a bound on nodes, which uses the bound on pairs and consider all of the other nodes in the opposite direction. Now let's go back to the first example when FMM is using the LB propagation. I go back to the same place where FMM had to expand the G1 nodes before being able to expand A and C. The priority of G1 was equal to 3. But now, let's consider the LB values. The LB value of the pair A and G1 is induced by the F value of A, which is equal to 4. The LB value of S2 and G1 is induced by the sum of G values plus epsilon, which is also equal to 4. This is why the LB value of G1 is equal to 4, and since the LB propagation makes the F value become equal to the LB value, the F value of G1 is become 4, and the priority is updated to 4. So now, FMM does not need to expand G1, and it can continue to expand A and C and terminate. What about the second example? So I'll go back again to the same place where FMM had to expand D. This time, the only other node in the opposite direction is A, and the F value of A is equal to 4. That is why the F value of D becomes 4 as well, and FMM can choose to expand A and terminate. Let's move on to GBFHS. So the first running example remains the same, so we'll go back to the second example. And the same thing happens here. Because of the LB values, the F value of D becomes 4, so the F limit is now incremented, and GBFHS can choose to expand A and terminate. Since the LB enhanced version of the algorithms did not have to expand the D node in the second example, while the original algorithms had to, the M and E values of the enhanced algorithms are strictly less than the M and E value of the original algorithms in this example. Moreover, we have a theorem in the paper that states that for every problem instance I, the M and E value of the LB enhanced versions is less than or equal to the M and E value of the original version. Finally, we showed that DFMM-LB and GBFHS-LB are equivalent in the sense that they expand the same set of nodes in the same order when given the proper parameter mapping. So given DFMM-LB with a fraction p, an equivalent GBFHS-LB will have the following glim forward and glim backward values. And on the other end, given GBFHS-LB with F-lim, G-lim forward, and G-lim backward, an equivalent DFMM-LB will have the following fraction. This means that for every problem instance I, the M and E values of both algorithms will be the same. And you can find the full MNE hierarchy of the different algorithms in the paper. To conclude, I would like to mention a couple of things that I did not cover in this talk. First, both FMM and GBFHS have some very interesting theoretical properties proven for one but not the other, and the equivalence between their variants suggests that these variants share the same properties. Second, I did not mention anything about runtime, but just know that all the variants require similar computational resources, except for FMM with a constant fraction that has a smaller overhead. So that's it, I'm done, and I'll be happy to answer any questions you might have.